engineering drawings, tolerance modifiers. Where you have a tolerance, which is the amount of permissible variation in dimension, there are modifiers. The maximum material condition, with the acronym MMC, is the condition of a dimension where the most material allowed by the tolerance is still there.
Datum features B and C have been modified at MMC. This doesn't change the profile tolerance zone, which is still 0.4. It does allow the profile tolerance to float a bit when the datum features are made larger than their virtual condition. Let's say this part is to be inspected using an overlay on an optical comparator. If datum features B and C had been applied RFS, the part shadow could not move or float on the datum simulators. Since datum features B and C are modified at MMC, the overlay includes the virtual conditions of the datum features, shown here in red. An inspector could float the outline of the part around to bring it into the profile zone of 0.4, provided the datum features did not violate their virtual conditions.
The maximum material condition is the condition in which the size of a feature contains the maximum amount of material within the stated limits of size. The example given here includes a minimum hole diameter and maximum shaft diameter, both of which result in the greatest possible amount of material being used. Next, we'll discuss the least material condition as referenced with the example on the right-hand side of your slide. The least material condition is the condition in which the size of a feature contains the least amount of material within the stated tolerance limits. The example here includes a maximum hole diameter and a minimum shaft diameter. For the hole in this example, the hole diameter varies between 0.456 and 0.464. At the maximum material condition, the hole will measure 0.456. At the least material condition, the hole will measure 0.464. For the shaft referenced in this example, the shaft diameter varies between 0.456 and 0.464. At the maximum material condition for the shaft will measure 0.464. At the least material condition, the shaft measures 0.456. Hole shaft bonus tolerance example. Bonus tolerance. A bonus tolerance is an additional tolerance for geometric control. Whenever a geometric tolerance is applied to a feature of size and it contains an MMC or an LMC modifier in the tolerance portion of the feature control frame, bonus tolerance is permissible. Slide 24, applying tolerance modifiers. The M in the feature control frame means that the tolerance applies only when the hole diameter measures 0.495, which is the maximum material condition. As the hole diameter increases towards its upper limit, additional bonus tolerance is allowed. So in essence, total tolerance equals tolerance at maximum material condition and bonus tolerance. In this slide, the M in the feature control frame means that the tolerance applies only when the shaft diameter measures 0.464, which is the maximum material condition. Because the shaft diameter decreases towards its lower limit, additional bonus tolerance is allowed. Next, we will be discussing geometric characteristic symbols. On this slide, you will see some of the characteristic symbols that we will be discussing in the next few slides. Geometric characteristic symbols. Straightness. A condition where all points are in a straight line, or the tolerance specified by a zone formed by two parallel lines. Flatness. All the points on a surface are in one plane, or the tolerance specified by a zone formed by two parallel planes. Roundness or circularity. All the points on a surface are in a circle. The tolerance is specified by a zone bounded by two concentric circles. Cylindricity. All of the points of a surface of revolution are equidistant from a common axis. A cylindricity tolerance specifies a tolerance zone bounded by two concentric cylinders within which the surface must lie. Profile. a tolerance method of controlling irregular surfaces, lines, arcs, or normal planes. Profiles can be applied to individual line elements or the entire surface of a part. The profile tolerance specifies a uniform boundary along the true profile within which the elements of the surface must lie. Angularity. The condition of a surface or axis at a specified angle other than 90 degrees from a datum plane or axis. The tolerance zone is defined by two parallel planes at the specified basic angle from a datum plane or axis. Perpendicularity. The condition of a surface or axis at a right angle to a datum plane or axis. Perpendicularity tolerance specifies one of the following: a zone defined by two planes perpendicular to a datum plane or axis, or a zone defined by two parallel planes perpendicular to the datum axis. Parallelism. The condition of a surface or axis equidistant at all points from a datum plane or axis. Parallelism tolerance specifies one of the following: a zone defined by two planes or lines parallel to a datum plane or axis, or a cylindrical tolerance zone whose axis is parallel to a datum axis. Concentricity. The axis of all cross-sectional elements of a surface of revolution are common to the axis of the datum feature. Concentricity tolerances specifies a cylindrical tolerance zone whose axis coincides with the datum axis. Position. A positional tolerance defines a zone in which the center plane is permitted to vary from true, or theoretically exact, position. Basic dimensions establish the true position from datum features and between interrelated features. A positional tolerance is the total permissible variation in location of a feature without its exact location. For cylindrical features such as holes and outside diameters, the positional tolerance is generally the diameter of the tolerance zone in which the axis of the feature must lie. For features that are not round, such as slots and tabs, the positional tolerance is the total width of the tolerance zone in which the center plane of the feature must lie. Circular runout. Circular runout provides control of circular elements of a surface. The tolerance is applied independently at any circular measuring position as the part is rotated 360 degrees. A circular runout tolerance applied to surfaces constructed around a datum axis controls cumulative variations of circularity and coaxiality. When applied to surfaces constructed at right angles to the datum axis, it controls circular elements of a plane surface. Total runout. Total runout provides composite control of all surface elements. The tolerance is applied simultaneously to circular and longitudinal elements as a part is rotated 360 degrees. Total runout controls cumulative variation of circularity, cylindricity, straightness, coaxiality, angularity, taper, and profile when it is applied to surfaces constructed around a datum axis. When it is applied to surfaces constructed at right angles to a datum axis, it controls cumulative variations of perpendicularity and flatness. Important dimensioning and tolerancing definitions. Datum. A reference point, surface, or axis on an object against which measurements are made. Datum simulator. A surface of adequate position oriented to the high points of a designated datum from which the simulated datum is established. Examples of these are surface plates, gauge pins, and ring gauges. Interference refers to the fact that one part slightly interferes with the space another part is taking up. Interference fit, which is a press fit. A fastening between two parts which is achieved by friction after the parts are pushed together. Parallelism versus flatness. With parallelism, a reference is made to a datum plane, while flatness is independent of a datum. Tolerance. The total amount by which a specified dimension may vary, or the difference between maximum and minimum limits.